Good afternoon. So welcome to LabSits. I hope I'm audible. Yeah. Okay. So the agenda for today's lab is to go over generative models, and so I mean, up until a couple of years ago, GANs was the primary generative model that everybody relied on, to state of the art in almost all generative tasks you could think about. But then recently, I mean, you guys should have come across this as well, probably. But then you must have seen diffusion models, and diffusion models are insanely good right now, and I'm pretty sure they'll only get better and better. But for the lab, so I mean, like you can't do generative models without talking about GANs. So we'll do GANs, but then because diffusion is so good right now, we'll just have a look at diffusion as well, but not in depth. We'll just have a uh, basic discussion on what diffusion actually is, and not get into the depth of it, because first of all, it's not really possible to train on Google Colab, and plus I think if you're going to if you're going to tackle a general, like a very general generative task, then it's usually a good idea to stick to GANs for the time being. And so yeah, so our goal today, the first goal today, is to deal with GANs. Okay. Yeah, let me switch to GPU runtime. What am I doing? Yeah. Okay. So okay, let's. So for, I don't think Sir has covered GANs in his lab. So the first thing that we'll do is we'll go over what a GAN is and how it works, and then we'll go into the code. So right. Okay, wait, let me open it in my browser. All right. So you have a generated model and you have a discriminated model. So the first thing that you have to keep in mind in GANs is that there are two models. There are two neural networks. The first neural network is called a generator, and the second is called a discriminator. And two of these neural networks work hand in hand. The generated model, the goal of the generated model is to generate whatever you want to generate. So, like in case you're planning to generate an image, or if you want to generate text, or whatever it is that you want to generate, that is done by the generator model. So generator model takes in a random input. It's usually called a latent vector, and it's random in the sense that there is no specific meaning per se to the vector that you're going to feed into the generator. So unlike in our case when we do classification, the input to the neural network is what? The input to the neural network is a image, and you're classifying it. Or in case of segmentation, again, it's an input is the image. In case of when we did text semantic, when we did semantic analysis of text, uh, so in that case, the input was text, which we encoded in some format. And same thing when we use transformers as well, the input was meaningful. But in this case, in case of GANs, the input of the generator is random in the sense that there's no meaning to the input, and it's and the input size is like you can decide the size. It can be 512, uh, single dimensional 512 size input, or maybe 256, 128. It depends on what you're trying to do. So you pass in a random vector to the generator, and the goal of the generator is to use this random vector as a input, and to generate whatever you want to generate. Maybe you want to generate images of tigers. Maybe you want to generate very specific things. Whatever you want to generate, maybe you want to generate text. Regardless of what you want to generate, you pass in some random input, the generator generates the text. Now that is, and that's what we eventually want. We want the end goal of training is so that we finally have a generator that is able to do this. But the generator alone cannot do this, because like what laws do you expect to use here? Like if you pass in a random input and you get the image of a tiger, and then like what laws will you have that will specify, that will tell the generator that the image of a tiger that you've generated is good enough? And there's no tiger laws that we know of so far. And so what in this case, what we have to do is we need a second neural network called and which is referred to as the discriminator. And so what the discriminator does is it takes in images and it classifies whether it is a real image or a fake image. And what do you mean by real image or fake image? By real image, you mean a image that has not been generated by generator. That means a real world image. So like a real image of a tiger that you would click with the camera is the real image. And the fake image would be what is generated by the generator. Now, the job of the discriminator is to take in different samples, which can be real or fake, and then decide if it's real or fake. And the loss of the discriminator will be then what? It will be binary cross entropy because, I mean, when you do a binary classification problem, we've done this before as well. You're doing a binary classification problem, then whenever you're doing any kind of classification problem, you use cross entropy loss. Like this is the fifth time we have been doing it, so you guys probably know this. And so in this case, we are doing a binary classification problem, whether it is real or fake. And so in this case, we'll use binary cross entropy loss for the discriminator. Now, so the goal of the generator is to fool the discriminator. And so eventually, through the course of training, the goal is to make the generator good enough so that it can fool the discriminator, meaning that the discriminator should be unable to discriminate between real images and images that have been generated by the generator. And the goal of the discriminator is to get good enough so that it can discriminate between real images and generated images. So it's kind of a tug of war, if you can think about it like that. And like, so imagine, so there's a problem with GANs because of this very fact. If the discriminator is very good, imagine the discriminator is extremely good that it always discriminates between real and real images and generated images. In that case, it will overpower the generator in the sense that the generator is not able to fool the discriminator in any case, and so it's not getting any meaningful signals as to like. So generator eventually has to imagine you want to generate the picture of a tiger. Now the generator does even when it starts training, it's random weights, right? The generator does not know what a tiger looks like, how it can generate the image of a tiger. So if it generates an image and the discriminator says that it's fake, every time if the discriminator says that it's fake, then the generator is not getting any useful signals through backpropagation, right? So like the generators can't. But imagine the discriminator is imperfect. So imagine the discriminator sometimes make mistakes. So the discriminator is sometimes fooled by the generator. In that case, the generator understands that when it generates images of some type, so so the generator understands that if it generates images that look somewhat like a tiger, then it can fool the discriminator. So eventually, as the generator and the discriminator become better and better, the generator starts generating images that can fool the better and better discriminator. And so eventually it will start generating images that look more and more like a tiger. That's the whole idea with GANs. And a very important thing that you have to stress on is that while you're training a generator, you have to ensure that neither your generator nor your discriminator is getting too good, because then there's no useful signals passing through the discriminator from the discriminator to the generator. And the generator is not trained directly, the generator is trained through the discriminator. So the goal of the generator is to fool the discriminator, right? So the discriminator wants to minimize his cross entropy loss, and the generator wants to maximize the discriminator's cross entropy loss. So the weights of the generator are modified according to this loss, but then so the weights flow through this channel like this. You're not directly There's no direct loss directly for the generator. I hope that's clear. I mean, it's pretty simple. You have a generator, you have a discriminator. Generator generated images. Discriminator decides if it's fake or real. And based on the signal, the generator gets better and better at generating images that look very real. And so the reason why this latent vector, this random input that we pass in. So uh, our goal is to generate different images each time, right? We need diversity also in the tiger images that we generate. We do not want the generator to create one image every time, which would be pointless. The whole goal is diversity. So what we do is, so that is why we have this random input. So based on how we modify this random input, like we can have different random inputs that we pass to the generator, and so based on the different random inputs, you get different images of tigers. And so again, to reiterate, the goal is so that the generator does not end up just generating a single image of a tiger, but then it learns to generate what a tiger looks like. So the goal is that the generator learns what a tiger looks like, essentially, the entire data distribution of tiger images, so that it can, in theory, generate any tiger image. Okay, that is the basic theory behind generators. And what we'll do now is we'll also look at the laws for generator laws for this whole thing, which is important. Okay, it's not going full screen. Yes. So it might look complicated, but it's extremely simple. So there's this V, which is some kind of a loss, and there's a min. So you can see there's a min here and there's a maths here, and so that's why it's sometimes called a min maths loss. It's called a min maths game. The training of generator is sometimes called a min maths game. The So this is not actually the loss. This is the negative of the loss. So the goal of the discriminator. What is the goal of the discriminator? The goal of the discriminator is to minimize this loss. Okay. And so when you take the negative of the loss, then that would mean the discriminator wants to maximize the loss, right? So if you want to minimize the loss, then you maximize the negative of the loss. So because this is the negative of the loss, the discriminator, which is D, wants to maximize it, and the generator wants to minimize it. Which, like what I was discussing earlier, the generator wants to fool the discriminator, so it wants to maximize this loss, which in turn means minimize this negative of this loss. This V, which is the negative of the loss. And let's look at, so it's basically cross entropy, but then done two times, because firstly the discriminator, there will be cross entropy on the real images. So when you're passing in real images to the discriminator should get should always output 1 corresponding to real, which is this. No, so which is this, yeah. So when you're passing in real images to the discriminator, which is X, when you're passing in real images, so X is sampled from the data, which means that the data distribution of real images, so real tiger images, there will be distribution of real tiger images. Let's call that P data. You're sampling X from that, and you are sampling X from that, and you're passing it to the discriminator. So the discriminator should return what? 1. And that is why there's this binary cross entropy term here, log of dfx. So imagine it's 1, and the discriminator outputs 1. In that case, the loss should be 0. But if it's 1 and the discriminator outputs 0, then there should be a loss, and vice versa. And that's the goal of this term, the first term. The first term is so that the discriminator outputs 1 on real images. Okay. Now, the second case, you taken an input, you pass it through the generator. Right? You taking your random input Z. It's called Z. Z, you're sampling from some random distribution. It can be a Gaussian, it can be whatever. Sampling a random Z, you're passing it through your generator, and you have a generated tiger image. Now you take that generated tiger image, you pass it through the discriminator D. Okay. And you pass through the discriminator, and what should the discriminator output? The discriminator should output 0. So 1 minus the output of the discriminator should be 1. Now again, it's the same thing. It's again the same binary cross entropy thing. So the discriminator should now output 0, and the true label is 0 because it's a generated image. The true label is 0. Whatever the discriminator outputs is G. I'm sorry, it's D of G of Z, and then it's again this binary cross entropy term, so that the discriminator can learn to identify fake images. Now, this is the entire loss term. This is the entire loss term. Like, is there anything that you have that's like not clear here? Yes, yes, yes. Data on the fake image. Yes, fake image should the discriminator should give 0 here. Yes, this should be 0. Yes. If DGZ is 1, you should record loss, which is what will happen. What is log of 0? Log of 0 is minus infinity, right? And so the goal of the discriminator is to maximize this. And so because you do not want it to go to minus infinity, you want it to be 0, the discriminator should output 1. But then the generator is like, no, but you should output 0, because the goal of the generator is to have the discriminator make mistakes. So it's both pulling in opposite directions. The min g is so that the generator wants this to output uh, wants it to output 1, but then the discriminator wants it to output 0 because it's fake. Yes. Yeah, log 1. I know. So if it outputs 1, then this will become log of 0, which is minus infinity. Uh, yeah, yeah, which is very high. And your discriminator, the goal of the discriminator is to maximize this thing, right? The goal of the discriminator is to maximize this thing. So minus infinity is not exactly maximization. And so it would rather have it be 0 than minus infinity. Because, I mean, so wait, let me go back to the image. Okay, not here. So what do you eventually want to do? You eventually want to generate extremely good image, good like real life looking images, right? And so eventually the generator should generate such good tiger images that the discriminator is fooled. And so when does that happen? It happens when the discriminator is making maximum errors, right? So eventually the generator should get so good that the discriminator cannot say whether it is real or fake. And so the discriminator wants its loss to be as small as possible, but the generator wants to maximize the loss of the discriminator. Yeah, and it does so by where is the loss? I think I closed it. And so the generator is only focused on this term. The generator just wants the discriminator to make mistakes. And so if when it makes mistakes, what will happen when it makes mistakes? The output of this d here will be 1, and when that output is 1, it becomes log of 0 or like something very close to 0. And so because of that, this will become a very negative term, and the discriminator does not want that. Discriminator wants it to be maximum, and then generator wants it to be minimum, which is why which is why I was saying it's like a tug of war. It's like a min match game. It's like the discriminator gets tiny bit more better, and then the generator gets tiny bit more better, and then the discriminator gets tiny. It's incrementally, so the discriminator and the generator incrementally become better and better, and eventually, what happens is the generator gets so good that the discriminator is fooled all the time. Yeah, that's pretty much the theory behind generators. It's pretty easy like this. It's very intuitive if you think about it. It's like when you have a generator, so the generator is being told if the image that it's generating is good enough or not through the discriminator. There's no direct signal, there's no direct supervision. It's through the discriminator that you get the signal. Yeah. Okay. So now we can go to the code, I think. And so we'll implement a extremely simple GAN because we it's just for demonstration purposes. It's pretty easy. And so the data set we'll use MNIST, and we'll stick to zeros and ones. So the MNIST has just give me a minute. Okay. Sorry for that. So I mean, yeah. So we've worked with the MNIST data set like 3 times now. I think 3 times now, and you know what the MNIST data set is already. It's a data set with digits, and so what we're gonna do is we're gonna take zeros and one the images of zeros and ones, and we're gonna make a GAN. We're gonna make a generator which learns how to generate zero images of zeros and ones. We sticking to zeros and ones because our model is pretty simple, and we don't want to train for a long time. So we'll stick to zeros and ones for now, and we'll make a simple generator and a simple discriminator which learns how to do this. Okay, input torch. Wait, let me see if I switched on the GPU. Yes. By okay. Now The first thing that we need is, of course, the dataset. So let's get the dataset. And if you remember, the dataset is already there in torchvision.datasets. Torchvision.datasets has MNIST. And we did this in the first lab as well, I think, when we did digit classification. Yeah. So we need this. We need um, transforms. Cool. So torchvision.datasets has MNIST, so we don't have to do any of the heavy lifting. It's already there. It's already implemented, so we can define like train and test sets directly. And this is the same thing that we did in the first lab. And now we need a target transform. Okay, we'll do that. Let's keep that none for now. I'll add it in. So, I mean, we need a one hot encoding vector, right? Like as always, when you do classification, we do one hot. So I'll have a function which uh, does the one hot encoding. I'll implement it, but let's define the dataset for now. Okay. Now we need a function which gives you the one hot encoding of the labels. So corresponding to your classes. So our classes will be, in this case, we are only dealing with zeros and ones. So your classes will be just 0 and 1. And your, so what will one hot encoding vectors for this look like? So in case you have 0, it will be a 0, it will be a 1 comma 0 vector. So wait, I'll do it. Let me add text. So imagine you have a list of labels. So 0 comma 1 comma 0 1 1 0, and this is corresponding to each image. So like the first image has a label 0, second image has a label 1, third image has a label 0, and so on. And when you convert this into a one hot encoding vector, what will this look like? It will be a list of lists, right? Wait, let me copy paste it. Yes. 2 3 4 5 6. Yeah, and this will be 1 comma 0 0 comma 1 0 0 comma 1 0 comma 1 1. You should be pretty familiar with what one hot encoding and one hot encoding is now. So we have two classes, which is 0 and 1. And so one hot encoding means that we'll, for corresponding to each label, we'll have a vector of size the number of classes. In this case, 2. So corresponding to each of these, we'll have a vector of size 2. And so once you convert it into one hot encoding vector, corresponding to 0, you'll have 1 comma 0, because it's 1 at position 0 and it's 0 elsewhere. And then for 1, you will have 0 comma 1, it's 1 at position 1 and it's 0 elsewhere, and so on. You have done this before as well, so I'm not going to explain it more. So we need a function that does this. So we'll define a function, one hot, it takes in labels. Labels. In our case, the length of class is 2. And we can just pass this in here. Cool. So now we have a train and test dataset, and it will be converted into tensors, and it will be converted into one hot encoding representation, which is what we want for when we're passing it through the loss. Eventually, we want it to be in this format, if you remember. Yeah. Okay. So now we have the dataset. So let me add a dataset is ready. Now what we need is we need a sampler. So for that, okay. So need a sampler. So why do we need a sampler? So in the dataset, in this MNIST dataset, there are images of all classes from 0 to 9. But because we're only dealing with two classes, we need to sample images from this dataset that belong to these two classes. So typically what we do is you use a random sampler from torsion.utils.data. But then because in our case we want to just sample those belong to these classes, we'll have to slightly modify the sampler. So first let's import stuff. So from torch.utils.data.sampler import and hope I did that right. Yeah. And now what we'll do is we'll make a function. Yes. Sahil. Yeah, sorry. This is fine. Okay. So what was I saying? Yeah, okay. So now that we have the data set and we need to sample samples from it that belong to just these classes, what we'll do is we'll build a sampler. And the goal of this sampler is that it only takes data points that are belonging to these classes. So there'll be images corresponding to all digits, but we just want 0 and 1. Okay, so I'll write something and then I'll explain. So for I in classes. Okay. So what we're doing here is basically we are so what we want is a sampler that gets only zeros and ones, gets samples that have classes zeros and ones. And so we use subset random sampler, which is there in torch.utils.sampler, and we need to pass the indices of the labels that correspond to these classes that we want to sample from. And so to get these indices, what we're doing is we're just we're just looking at we're just looking at the label, and if the label is one of the classes that we want, then we choose it. And so this is just a lambda. Oh, fuck. Yeah. So this is wait. I'll just show you in action. That will be better. So if I do so let's say we have a label tensor, and we have 102901, and so we only want to pick up this and this, because we are only choosing zeros and ones. And so we'll do what we can do is, if we do this, yeah, this. Okay, I did not import it. What you'll get is, so you'll get true corresponding to the places where it is in classes. If I is in class, which basically means if it's 0 or 1, you'll get true. Otherwise, you'll get false. And uh, okay, so what happens here? So I'll just explain it in uh, you know. So wait, I'll so first let's say one. You take one. There's one in 0, 1. It is in 0, 1, and so you'll get a. So this list will be what? It will be false, true, because it's checking if I if the label is equal to I. So first it'll check if it's equal to 0, and then if it'll check if it is equal to 1. If is it equal to 0, it is not equal to 0. So you'll get false, true. You'll get false, true. Basically, you'll get list. It'll be a list, not a tuple. It'll be a list. You get false, true, and then you take this list and you apply this lambda. And what reduce does is it so it applies it one by one. So in case you had like false, true, false, true, false, then it'll take x or y. We're doing x or y here, so it'll take false and it'll OR it with true. It'll take the result and it'll OR it with false. It'll take the result, it'll OR it with true, and so on. So in our case, we'll have false, true. So what will happen is it'll take false and it'll OR it with true, and false or true is true, which is what we'll get here, true. And then it'll do that for all the everything that we're passing in. That is what is happening here. And when we do np.var just yeah, so np.var just converts this into indices. So essentially, what we want is the indices where it is 0 or 1, and that is what we're gonna pass to our random sampler. So the subset random sampler wants the indices in the dataset where the label is the label that we want. Okay. Yeah, I think I might have confused you guys on that, but then if you have a doubt, please do ask. All that is doing is it's just so the sampler, we are modifying the sampler so that we are getting the samples from the classes that we want. That's it. Okay, so now we have our sampler, we have our data set. Now we need loaders, we need data loaders. Yeah. Data loader. So let's have a batch size of 64. We'll have a train loader. Train loader, which is, oh, we haven't imported that. So torch dot, yeah, torch dot from torch dot utils dot yeah, so it'll be a data loader. Data loader, no, data loader. We pass in the data train set, batch size, sampler, the sampler that we made, which is stratified sampler of and we'll have a test loader as well. So this is just a data loader, like there's nothing to explain here. It's just a data loader that you're making, which will load samples from the dataset. It will use the sampler that we just made, the stratified sampler. And for the test loader, test batch size can be 64. Samplers, same thing, but then and now we have that. Now all that remains is the model itself. I mean, excluding the training script, of course. Now we need a model. We need a generator, and we need a discriminator. So let's import NN first. We're gonna implement neural network, so we need NN. Now we need two things. First, we need a generator, and then we need a discriminator. Now in the generator, what is the first thing that we need? The first thing that we need is we need to decide on what will be the dimensionality of this input that we're passing into this latent vector that you're passing into the generator. We need to decide what is the dimension. You can choose whatever you want. It doesn't really matter. So this latent dimension, let's choose that 100. Okay, so now we need a generator. And again, our discriminator will also be a sequential. Okay, we'll have two models. Loss will be binary cross and PE loss. Right. You'll have to. So okay, now let's fill in this. I mean, the actual model does not really matter. Like there are probably like hundreds of GAN papers at this point. Like if not hundreds, thousands of GAN papers. And so each paper, each architecture will be different, and it really depends upon what you're trying to do. If you're trying to generate like huge images, if you're trying to generate tiny images, what is the variety in the kind of images that you're trying to generate? It depends upon a lot of things, and so the neural network architecture is very flexible. You can have convolutional neural networks, you can have transformers. There are transformer based GANs that you can use. You can use whatever you want. And here I'll just have a very simple model. Okay, so I'll have to fill this in now. Transpose 2D, yes. You guys can take 5 minutes break if you want. This will take some time. I'm just gonna add in the layers. Okay, same thing again. This time we want to go from 256 to 28. Oh, so I don't think we have discussed transpose convolutions yet. I mean, it's not really important. So in convolutional transform in convolutional layers, what usually happens in convolutional layers, you go from higher dimension. I mean, higher spatial dimensions to lower spatial dimensions. So like eventually you'll start with like a say 100 by 100 image, and then eventually it'll become like maybe 50 by 50, and it'll become smaller and smaller. But in our case, because we're starting with a 100 dimensional, a single like 1 by 100 thing, starting with a something that's like 1 by 100. I mean, this is very low dimensions, right? So you can't really go on reducing this and expect to get a image. And so what you do is you use con transpose 2D, and con transpose 2D does the opposite of what transform. I mean, convolution basic. I mean, like no, so normal convolutions do. It goes from a lower spatial dimension to a higher spatial dimension. But it's sometimes called a fractional stride convolution or something like that. But yeah, the actual mechanics is not important. But yeah, that's what it does. Instead of going from higher to lower spatial dimension, it goes from lower to higher spatial dimension. Okay. Finally, I have a sig point. I just put two devices here. Okay, I think so. You go from the later dimension to 256, and then you go to 128, and then you go to 64, and then you go to single final because it's black and white, right? And MNIST the images are black and white. You don't need three channels. You only need a single channel. And yeah, and discriminator. So discriminator, you will use normal convolutions because it's going from higher to lower, right? Discriminator. The goal of the discriminator is to finally take the image, which is high spatial, like 100 by 100 image, and then it goes to down to a single value, basically 0 or 1. So in this case, we want to use normal convolutions. We want to progressively decrease the spatial dimension. So we'll use a normal convolution and dot conv 2D. fact that we're using leaky ReLU here and not ReLU here has to do with the fact. I mean, it's better for training the discriminator. So I mean, these are small things that are important, but then it's not important in the big picture. When you look at the big picture, but then the thing with GANs is, and it's also an advantage with GANs. It's very you could say sensitive. It can fail. You like your training can fail, and it's very sensitive, I think, to hyperparameters. And it's basically a pain to train GANs and to finally get correct results. I mean, when you're dealing with MNIST, it won't be that big of a deal. But when you're dealing with like big data sets, you want to generate like, I don't know, big high dimensional realistic hyper realistic images. Training a GAN is not exactly the easiest thing to do, because you'll have to like play around with all kinds of activations and everything. Yeah. Yeah, another thing you probably yeah, never mind. Okay. That was not fun. We have a discriminator and generator, and like I was saying, the actual architecture is not really important. Just understand that you have a generator that takes in a latent dimension sized vector, and you finally get an image, and the discriminator takes in the image, and you finally get a single value and a single dimensional single value, basically, which tells you whether it is a real or a fake image. That's a one or a zero. And yeah, that's pretty much it with generator and discriminator. And now laws, you're using binary cross entropy laws because that's what you're doing. I mean, that's essentially what you're doing with the discriminator, and indirectly with the generator also, it's binary cross entropy laws. We'll see how you're going to use it. Okay, now what something else that we need is the optimizers, generator optimizer. And because so this time we have two neural networks instead of having single neural networks. You have two neural networks, and when you have two neural networks, you have the weights corresponding to the two of the neural networks, separate weights, right? It's not a single weight, single set of weights. So you need, because you're optimizing the two neural networks at once, you need two optimizers, because yeah, because you're dealing with the weights of two neural networks. Pretty self-explanatory. One works on the parameters of the generator and the learning rate. You need a optimizer for the discriminator as well. Discriminator. Mm, yeah, should be fine. So now we have everything. We have our data set, we have our sampler, we have a data loader, we have the model, we have a loss, we have the generator and the discriminator optimizers. We need the optimizer to optimize the weights of the corresponding networks. So yeah, so now training. Okay, so let's say we'll train it for 50 bucks. Did we? Yeah, we did. Okay. So I'm only interested in the image itself. I'm not interested in the label. And by label, so the label, the fact whether it is a zero or a one does not is not important to us. But then a label in the form of whether it is real or fake would be important to us. What is important to the generator is not whether it is a zero or a one. What is important to the generator is whether it is real or fake. So we do not need the labels in terms of whether it is zeros or ones, which is what we'll get from the train loader. So which is why I ignored it here. Okay, so let's have a list, two lists. Discriminator, wait, discriminator loss. The same thing for generator. Um, so this is one epoch and this is one iteration, one batch. So this will give you one batch, and now we have to do the entire training for that single batch. Okay, so the batch size will be first dimension, which is 64 in this case. It will be 64 in this case because we've specified it to be 64. Um, okay, yeah. So I have not really done anything till now. So you just extracted the batch size from the. So the train loader will give you a batch, right? One batch at a time, and so the batch size will be the first dimension of x of whatever the train loader is giving you. And the true label, is so what you're gonna do. Wait, I think I should explain this once I actually write the loss calculations. First we will send the real data to the discriminator. Discriminator. Okay, so what so all the images that are given by the train loader are real images because it's from the dataset, it's from the MNIST dataset. These are real images, right? These are not the images that your generator has created. All the images that will be given by your train loader, all the 64, the batch size number of images, all the images in H will be real images. So what will be the label for it? The label for it will be one. The ground truth label for it should be one. And so the goal of your discriminator is to do what? The goal of your discriminator will be to predict one for all of these real images. For all of X, the discriminator should produce one. So I'm taking X, I'm passing it to the discriminator. The output is what? Output is I'm storing it in output, and then the error corresponding to the true images, the ground truth. I mean the real images will be binary cross entropy between the output and true label, and that is why I made a true label which is of size batch size. What is this? The true label is 64 comma 1, and it's all ones. And why is it all ones? Because the labels for all ground truth images should be one. The For real images the label is one, and so the true label will be just a one will be just like a 64 comma 1 dimensional vector of just ones. Okay, so the ground truth is all ones, and output is whatever your discriminator is predicting on the input on the images. So you're passing in the real images through your discriminator, and you want your discriminator to predict 1, and which is shown in this true label. And so then you're passing both of them through the binary cross entropy loss that we declared earlier. That is for the first thing. So first you're passing the real images to the discriminator, and then we'll do to dot backward. We'll propagate the gradients backward. Okay. Now step 2, second step is to generate fake data and pass it through the discriminator. So now we first passed in the real images. Now we'll generate images and then we'll pass it through the discriminator. And what do we need for generating images? For generating images, we need this random input Z. So we'll make a random input Z. We'll torch.rand and latent dimension. So what this will do, I'm gonna generate batch size number of latent vectors, each of dimension latent dimension. Latent dimension is 100 in this case. We can generate 64 vectors of size 100, 100, 1, 1. And then this will be your latent vector that we're going to pass to a model. And so what we're going to do now is we're going to take this and we're going to pass through a generator. So generator, pass through a generator, and that will be its fake, the fake images. First I have to and we do not need to calculate gradients for this because we're generating it. Yeah, we're generating it right. This for the generate. I mean, so for the generation of the Z, the gradients need not to be calculated because Z. So finally our goal is we need to be able to pass in like any Z and get a tiger image, and the value of Z does not really matter. The what matters is the fact that you're getting a tiger image. So we do not really need to calculate. We do not have to calculate weights corresponding to generating Z. So that's why I've done Z dot requires grad is false, and then I've put it on the GPU. And then what I've done is I've passed the latent vector through the vectors. Actually, see batch size number of latent vectors. I've passed it through the generator, and what will I get? I'll get fake images. Now what do I do? Now I take this fake images and I pass it through the discriminator, and the discriminator will be should ideally discriminator should ideally predict zeros. So I'll take my discriminator and I'll pass my fake through it, and I'll detach because I do not want to update the weights of the gradient. The weights of the gradient we do not update directly. We update it when we update it after through the discriminator. So like I was mentioning, we do not directly. So the loss does not directly affect the weights. It affects the weights through the discriminator. What the discriminator does is what affects the weights of the generator. And so I've detached it so that when we do fake dot backward, we only want the weights of the discriminator to change. We do not want the weights of the generator to change because now currently we're training the discriminator. So detaches it from the compute graph. Oh. And now what do we have to do? We need to calculate the fake error. And what will be the fake error? The fake error will again be binary cross entropy. It's the same thing you're doing binary classification, so it will be binary cross entropy. You take your output, and what should be the labels? The ground truth labels should be zeros. It should all be zeros because it's all fake images that you've generated using your generator. And now you have calculated the error. You do error fake dot backward. Okay, so now you have done training for the discriminator. No, you haven't done training for the discriminator. You have to have a step for the optimizer as well. So you take discriminator optim dot step. Okay, now training the discriminator is done. So you took in the real images, you passed them through a discriminator, and you calculated loss, and you gave the true labels as 1 because it's real images. And then you generated images using random vectors, using Z that you sampled from a normal distribution. You passed in through the generator, and you got fake images. And then you took these fake images, you pass it to the discriminator, and you calculated loss, again binary cross entropy, and you give zero. 0 as a label, ground truth label here, because it's generated images. Okay, and then you do discriminator optim dot step. You calculated the gradients in both cases, and then you do a step of optimization. The training part for the discriminator is done. Now what we're gonna do? Now what we're gonna do is we're gonna train the generator. Training the generator. So how do we do that? So we do the same thing, but in this case, so here, uh, yeah, we do the same thing, but in this case, we do not detach it. We want to update the weights of the generator. Yeah, sweet. We've taken the generated images, and you pass it to the discriminator. And this time when you're calculating gradients will be calculated for the weights. I mean, so the weights for the generator will also be updated, because now earlier what we did was we did dot detach. So in that case, only the discriminator weights will be updated. But in this case, when we're doing loss dot backward, weights will be calculated till here, and then we do generator optim dot step, and so the generator weights will be updated. I hope it's clear. So earlier what we did was we freeze the weights uh, for generator. We only updated the weights for the discriminator because we were training the discriminator. Now what we're gonna do is we're gonna take do this losses, the gradients will be calculated for everything, and then we do generator optim dot step. So the weights of the generator will be updated. I hope that's clear based on the gradients that we're calculating. Okay, so our generator loss will be loss of output. A true label. So why am I doing this? Why am I doing this? I'm doing this because I'm calculating binary cross entropy. And what does the generator want to do? The generator wants the discriminator to make a mistake, which means that it wants the discriminator to predict 1 when it's not 1. So my loss binary, so I'm doing binary cross entropy between the output of the discriminator and ones here. Earlier we did it with zeros because discriminator wants it to be 0, the generator wants it to be 1, and so the loss will force the generator to generate images such that the discriminator produces ones, but the discriminator on the other hand will get better and better so that it produces zeros corresponding when it's actually 0. But when it's 0, the generator wants the discriminator to fail, which means it wants it to generate ones when it's actually 0, which is why I've given true label here, which is all ones. I hope that's clear. If that's not clear, please do ask. Okay, so we calculated the error, and we'll again do error generator dot backward, and then we'll do generate optim dot step. So now the weights of the generator will be updated because we've calculated all the gradients still here, and then we'll do dot step, which will update the weights of the generator. Yeah. Uh, okay, so I think that's pretty much it for the training loop. So we did train the discriminator. We trained the discriminator again by passing the fake images, and then we wanted to train the generator. So for the generator, we passed in the fake images, but we did not detach because we want to calculate gradients for the generator as well. And then we calculated the loss, but this time we gave the ground truth labels as 1 because that's what the generator wants to do. And then we calculated the gradients, and then we did a step. Um, yeah, I don't think. Yeah, okay, so maybe we can keep track of the. So I'm just maintaining a list which will. So I want to keep track of the throughout the epoch. I want to keep track of the generator and discriminator loss, and then maybe we can average it and take a mean of it and add it to the this list. Same thing that we did when we did classification. If you remember, we had a batch list and a epoch list, and we kept adding the loss to it. But in this case, we have two losses because it's a generator and a discriminator. Uh, yeah. Okay. What is wrong here? Is it not indented correctly? Um, it's a problem in this line. Oh, all right. So there's. Oh, okay. I think I must have added something else extra here then. So that's this bracket is paired with this bracket. This bracket is paired with this bracket. Oh, okay. All right. So this should not be here. Is what you're saying? Hmm. Yeah, it's fine now. I think. Yeah. Cool. And then, yeah. Once this is done, loss. Right. Okay. Yeah. Spelling. Okay. That does not. Hmm. Yeah. So this is pretty much it for training. And yeah, I think now I'll just add some stuff that I found for plotting the thing as we go so that you can see how it works. So this is some stuff that I found. Okay, so we need matplotlib. Okay, so now I'll just add some code which does the visualization part. It's not really important. I'll copy paste it. Wait, let me see. Uh, let me see. Yeah, yeah. Mm. Oh, okay. Yeah, I copy it properly with the indentation. Should be fine now. Or not. Um, yeah, I think it's indentation. Yeah. I mean, yeah. Wait, let me see if this works. Okay, that's not working. Oh no. Yeah. Okay, let's run this. Hopefully nothing breaks. Yeah. 129 elements, not 128. Uh, so this is happening when you're calculating what true error, which is here. Yeah. And so that means it's something to do with. Oh, okay. Okay, let me go back and look at the model. Ah, right. It's 128. God damn it, I'll have to run it again. Uh, Hopefully it's fine this time. Hmm. Weird. It's not supposed to take this much time. Uh, okay. Um uh, Discriminator loss, NP dot mean on batch loss. So when I'm adding to batch loss, hmm, okay, I understand what happened. So I need to calculate the thing and then take dot item. Yeah. I need to take dot item of the whole thing because earlier what was happening was error two plus error fake dot item. So just only taking dot item for this single tensor, not the whole thing. And so there was still it is still attached. I think. Okay, let's see. Okay, let's go. Interesting. Okay. It's supposed to be much faster. I'm not sure what happened. I must have forgotten to do something. Ah, okay. I understood what happened. Uh, it was correct. It is being done for every epoch, which is what I want. Uh, hmm, I mean, usually in such a scenario, what I would have done is I would have opened up VS Code and I have put it there and I would have debugged it. But then because we're using collab, that's not really an option. Let's see. Oh wait, what? Wait, what? When did this image come? I didn't. Okay, let's try running it again. Okay, so let's keep this for running, and in the meantime, while it's running, let me talk about diffusion for some time. So yeah, so GANs had been the state of the art for like most, if not all, generative tasks. Especially images. Images. GANs have been like a big thing. Maybe like half of you guys have worked with GANs before. So but then in 2020, I think in 2020 it was UC Berkeley and OpenAI. I think they came up with. Uh, so I mean, it is an idea that had been existing before, but then they came up with a way to make it better. It's called something called a uh, denoising diffusion model. Something called a denoising diffusion model, and yeah. So I mean, so far we had. I'm not sure what Sarah taught you in class yet. So there are VAEs, variational autoencoders, is a kind of generative model, GANs, and now denoising diffusion models. They are kind of similar if you think about them from like a very broad perspective. But then how diffusion models achieve the goal of generating images is it's actually very interesting. Let me see if I have saved an image which explains this. Okay, yeah. So again, you take an image. Let's say, I mean, maybe not. This is not the best. Yeah, this one. You take an image of a cat, any image, and what you do is you add noise to it. It can be Gaussian noise. I think they typically stick to Gaussian noise, even in the papers that I've seen. You add noise, and you keep adding noise in incremental steps. So typically they do take like a step size of like 1,000 steps, but then you can choose what to do depending upon how much GPU you have, what and whatnot. Yeah, and so you take an image, a real life image, not a computer generated image. You take a real life image, whatever you want to generate. You want to generate cat images. Let's assume you take an image of a cat, you add noise to it, and then you add noise to it, and then you add noise to it, and so on. Incrementally, you keep add noising, adding noise to it 1,000 times. So like sequentially, and let's say you do it 1,000 times. So finally, you get pure noise. And now, what do you do? And this, there's no neural network involved in this process, right? In the forward diffusion process, there's no neural network involved. So, and there's no learning involved. There's no weights involved. Nothing. It's, you can do it on a CPU. Nothing. Yeah. So you do it, and then what you now the goal is, now you want to take this random noise and you want to go back. You want to go get this cat image, right? So now, I mean, it is kind of similar to GANs if you think about it, because in GANs you're taking a random noise basically. In the sense you're taking a random noise. I mean, you're not taking 100 by 100 dimensional random noise. So in case of diffusion, the spatial dimensions of the random noise that you're having is should be the same as the spatial dimensions of the image that you want to generate, right? And so when you're going backward, so first you keep on adding noise, you get this random noise, and then you want to go backward. And to go backward, what you do is you make use of a neural network. For that, you make use of a neural network. And what is the goal of your neural network? Your neural network will take this image and it'll predict the noise that was added in this step. So at time step 999 to time step 1,000, you added some delta, right? You added some noise to it, which converted it from 999 to 1,000th time step. Now, what the goal of your neural network is to predict the noise that was added from in this delta, so that it can subtract it. Okay. And so it predicts the delta, it subtracts it, it predicts the delta, it subtracts it, it predicts the delta, it subtracts it. The eventual goal is that you subtract, keep on subtracting, and eventually at 1,000 time steps, when you've undone generative reverse denoising process, when you've reversed it, you get a cat image. And the beauty of this is that depending upon what random image you start with, you get a different cat image. And so even like when you're done training a diffusion model, and when you do this backward, we start with like noise, and you apply the neural network sequentially to it, so that you keep reducing noise, to it, you eventually get a cat image. And like I was saying, the beauty of it is that based on the random noise that you start with, you will like get different cat images, which is kind of awesome in my opinion. Yeah. And I mean, you guys must have heard about like stable diffusion, which is uh I mean, like, it's insanely popular now. People do this text guided image generation, wherein they put in a prompt. So that's why I put a prompt in. Like, you can generate crazy images like this, like Putin looking at a dragon, kind of stuff, which is like it wasn't really possible before with like GANs and all. It was possible, but not like to this quality. uh yeah, so maybe I'd suggest looking into it, because it's really interesting. The math is also really important. It's like kind of inspired upon like thermodynamics, where like in thermodynamics you have the concept of increasing entropy or like decreasing heat, wherein your like it spreads out, right? Your entropy increases when you add noise, and that is basically what's happening. You're adding noise to this. And the important thing here is that you might think, so in the forward process, you do not have to do this sequentially, because so imagine you take this image, you add in some Gaussian noise, and then you add Gaussian noise to that, and you add Gaussian noise to that, and you might think, oh, we have to do this sequentially. It's slow because we have to do it for only after getting this we can generate this, which is not the case, because Gaussian noise, if you remember, sum of Gaussians is a Gaussian. So with just this image, you can parallelly generate all these time steps. Yeah, so like I'm saying, you can directly generate the 1,000 time step. You do not have to go sequentially, if you think about it. Yeah. So yeah. So wait. So if you guys want to play around with this, oh my god, what did I open? If you want to play around this with, this is a website called uh mage.space. It's free, I think. Okay, so I don't think I can. Maybe https mage.space. See if that works. Yeah, this is a website where you can like put in prompts, text prompts, and it will generate images for you. And yeah, and they use stable diffusion. They use a version of stable diffusion. Yeah, it's pretty interesting. And there are like very interesting videos on this on YouTube as well, and I suggest that you guys check it out, because the quality of images that you can generate using diffusion is insane. Okay. So our graphs have been generated. So let's go back. So we started with noise after one epoch of training. I don't think this. Yeah, this is one epoch of training. Our generator was generating this, and after two epochs, yeah, after two epochs, three, four, and so on. So you can see the generator gets better and better. Yeah, the generator loss initially increased because I think problem with the initialization maybe. But yeah, initially I mean the generator loss will decrease more and more, and you'll get better and better images of ones and zeros from your generator based on. So like basically what's happening is based on what sample. Wait, so in my visualization code, what's happening is you're generating a Z, and then you're passing it through the model, passing it through the generator, and you're getting fake images, and that's what is being plotted here. Yeah, and so like if your training is successful, if your training is successful, then so the thing with GANs is that training is not successful when your model converges exactly. It gets so you can't say when your model converges your training is successful, because in case of uh yeah, so like there's actually a quiz question on this, but yeah, maybe I should not explain it. Maybe you guys should think about it. Yeah, I mean it's pretty. It's not a difficult question. It's like an extremely easy question, but then you just have to think about what's actually happening. GANs. I mean, what's happening with the generator and the discriminator, and like when can you say that uh, it's doing a good job? When is your discriminator doing a good job? Like when can you stop training? Yeah. So I don't think I should keep training this. I mean, you get the picture, right? Your discriminator loss is decreasing. I mean, your generator loss is decreasing. That's what's important. The generator loss is decreasing. The images are kind of getting better and better. Yeah, and I mean, like, how much better can it get than this? Like, it's just generating black and white images of zeros and ones. So maybe you can play around with this. I think for I don't know what sir is making you doing this time for the project. But then if he's if you're like writing code for GANs or some stuff, I don't know what you're doing. For the project, I mean, for the paper presentation or something, I don't remember. When I took the course, I remember some of my friends writing code for some kind of GANs. But then, yeah, if that is what you're going to do, then you'll probably have fun with it because you can generate all kinds of images. Yeah, so I don't think I should train this anymore, right? Like, you get the picture. If you guys have any doubt, please do ask. Yeah, and diffusion. So I don't think diffusion. It's not really possible to implement a diffusion model and training on Colab. So I'm not going to do it. But I'd point you to a YouTube video which is awesome. Let me see. Let me find it. Mm, yeah, I found it. Found it. This video. I hope I'm pasting the right thing. Yeah. This video from Outlier. It's. I mean, if you want to get into the math of it, it's awesome. If you want a overview of what like a basic overview of basic like extremely simple diffusion models, you can watch this. Yeah, this is more mathy. The first one is more mathy. The second one is more implementation based, where he's doing implementation. You can look at that. Yeah, there's a notebook as well. There's a notebook as well on diffusion if you want to look at that. And I hope I copied the right thing. Let me. Oh, yeah, maybe I should have pasted this. Yeah, so that's pretty much it for today's lab. Like, I just wanted to do GANs and just like present the fact that diffusion models exist so that you guys look into it. Uh, yeah, and I hope you got like a basic idea of how diffusion model work. It's pretty simple, denoising. It's not simple. The math is not simple, but I mean, at least I did not find it simple. But the overall idea is pretty simple. Okay, so we have done GANs. So let's, if you guys do not have questions, we can do the quiz, which will again be 15 minutes. It's easy. It is MCQ, I think, mostly. Let me copy. Yeah, if you do guys have any doubts, otherwise I'll send the quiz link.